My name is Marc Gregoire. I work for Nikon, or Nikon, as you pronounce it in the States. I'm also the author of Professional C++, and the third edition has just been released. It includes C++ 14 features, and I saw it's available in the bookstore, so feel free to take a look. My presentation is about C++ AMP, which stands for Accelerated Massive Parallelism. Can I have a show of hands? How many people have heard about C++ AMP? Okay, pretty much everyone. Anyone using it in production code? Okay, 1, 2, nice. I was thinking, what is the best way to start a presentation on GPGPU computing? And I think that's with a demo. In fact, I will start with 2 demos to demonstrate the power of C++ AMP. The first one is the n-body simulation problem. What this does is you have a number of stars with each individual star has a certain mass, has an acceleration, and has a velocity. To calculate the position, the velocity, and the acceleration of any of the bodies, you need to calculate the interaction of all the other bodies on that one body. So this is an n-squared problem, so it's computation intensive, but it's highly parallelizable. You can calculate every body individually, so it's perfectly suitable for something like C++ AMP or GPGPU computing in general. So let's see. Let's first start by running it on the CPU. So at the top, you see the number of gigaflops that we are getting out of this CPU. This is a quad-core CPU with hyperthreading, so there are 8 cores. But right now, it's using a single core. So the first step to increase performance is to switch to using all the cores available in your machine. So we switch to a parallel library like PPL or Intel TBB. And now you see we have a healthy performance increase. We are getting around 30 gigaflops out of this CPU. The next step to increase performance that you can get on a CPU is to use the vector instructions like SSE, AVX, and so on. All modern CPUs have these. So if we do that and we combine that with the parallel version, then we get another nice increase. Now we are getting 40 gigaflops out of this CPU in this laptop. But that's pretty much it. Now our CPU is running at 100% of its power, and you won't get any more performance out of this for this problem. So let's see what we can do with C++ AMP. So this is a very straightforward implementation, converting our parallel implementation to C++ AMP, and you see we already have 74 gigaflops. But right now it's using the same number of bodies as I was using for the CPU version. If we just increase this, then we see that we're getting 65 gigaflops out of the integrated. I'm actually using the Intel integrated graphics for this one. So that's already not too bad. But this is, like I said, the straightforward conversion from a CPU parallel version to C++ AMP. If you use a more advanced mode, like the C++ AMP tiled mode, then you see now we are already getting 134 gigaflops out of this laptop GPU. And yeah, as you see now, it's perfectly parallelizable. This laptop also has an NVIDIA Quadro inside. So normally you should be able to use both of them at the same time, but there is something wrong with the configuration, and the number of gigaflops actually is dropping by a few, so not sure why that is happening. Normally you should be able to use 2 heterogeneous GPUs in parallel. So here is a screenshot of another machine that's more a desktop machine, a bit more powerful. This one has 6 CPU cores. And you see we get around 31 gigaflops out of the CPU. This machine has 2 AMD Radeon GPUs in it. And when we use both of them at the same time, then you see we are getting 1 teraflops of single precision performance out of these 2 GPUs. And these AMD Radeon HD 5800, it's not the most recent one. In fact, NVIDIA just released their Quadro K6000, and according to their specifications, you get around 5.2 teraflops of single precision out of a single GPU. That's, of course, theoretically, so you have to lower it a little bit. The next demo that I want to show is a cartoonizer. What it does, it takes an image or even a live stream video, and it makes a cartoon image out of it. This laptop doesn't have any webcam, so I can only show the static image version. First, we load our image, and here you can choose how we should cartoonize it. So there is a CPU single core implementation, but I'm not going to run it because it will take like a minute or 2 minutes, so I'm not going to wait for that. So let's run the multi-core version. I also want to show you put it on top. Just okay, so this is the multi-core version, and you see that all my 8 cores will be at 100% calculating, and it should take around 12 seconds or so, 8 seconds. So it took 8.2 seconds to calculate a cartoonized version of this image. If we switch to C++ AMP, then you see it takes 380 milliseconds. On a little bit more powerful machine, that means you can do this in real time with a webcam and have 30 frames per second. And you see if you cartoonize it on the GPU, the CPU, there is no spike, it's not doing anything. There is also something called warp. I will come back to that later, but I just want to demonstrate it. It's actually an emulator of a DirectX 11 GPU. And if you run it, this is actually running in software now. It's not using any hardware acceleration. If we run this one, you see it takes a little less than 2 seconds, while my own implementation in software took 12 seconds. So this is highly optimized emulator, but I'll come back to that later. So, yes, can you please use a microphone, or then question is recorded?
Why did the images look different? Was it cartoonizing the cartoonized version, or?
No. Actually, the GPU cartoonizer is even doing more than the CPU cartoonizer, because the result of the CPU cartoonizer was not completely cartoonized either. You still saw some of the picture through it. So, yeah. So that were the 2 demos. So let's now continue. Small introduction. So before 2005, you had something called a free lunch. So every year, processor would be becoming more and more powerful. Single-thread performance would increase every year. So basically, if you add a new feature to your application and it was a bit slow, you could just wait a year and then it will be more than fast enough. Unfortunately, since 2005, that's not the case anymore. Clock speeds actually have almost stabilized. They are not increasing pretty much. What CPU vendors are doing now are putting more and more CPU cores on one piece of silicon. That means single-thread performance stays the same. So what is the result of this? If you want to have scalable performance with current CPUs and future CPUs, you have to have parallelism. Either you do it on the CPU or on the GPU or on both. But there is nothing like wait a year and it will be fast enough. So that's finished. I have one slide on CPU parallelism. You can do that with vector instructions, like the SIMD, single instruction, multiple data. For example, you have SSE, you have AVX. Like I said, all modern CPUs have these. And the other thing you can do is using multi-threading. You can use frameworks like Microsoft PPL, the Parallel Patterns Library, or Intel TBB, threading building blocks. And in fact, if you use Visual Studio 2012, then there is an auto-vectorizer and an auto-parallelizer built in. The auto-vectorizer is enabled by default. Auto-parallelizer you have to switch on. Of course, this is a very hard problem for compilers, so there are a lot of restrictions that you have for your loops before that the compiler will vectorize it or parallelize it. So this is on the CPU. What about the GPU? You can either target NVIDIA GPUs using CUDA, but that software will not run on AMD GPUs. If you want to optimally target AMD GPUs, you have to use OpenCL. You can also use Direct Compute from Microsoft, but that's an HLSL, high-level shader language. It's more like a C language. It's not C++, and we want to use C++. And yeah, as the last bullet said, actually all three of them are more like C, so they are not really C++. There is not that much type safety and genericity using templates and so on. And another problem is, yes, it's hard. If you want to, if you don't know what hardware your software will run on, then you have to target both NVIDIA and AMD. So it means you have to learn two different technologies. So C++ AMP is a solution for this. It's actually an abstraction layer over your GPUs. It's pure C++, nothing C, so you have all the type safety, you have all the genericity in the form of templates. It's also not an extension. It's actually almost completely library code, except for two extra keywords, which are tile static and restrict, and I will come back to them later. And C++ AMP is available on all machines where you install VC Redist, so you don't have to install anything extra. The best thing is it's an open standard. So Microsoft designed it, but it has been, it's now an open standard, and Intel has an experimental implementation, and AMD also has an open source implementation since a couple of weeks. So as said, it's vendor independent. It works with AMD GPUs, it works with Intel GPUs, with NVIDIA GPUs, and everything that supports DirectX 11, it will work on. There is this fallback warp driver, which stands for the Windows Advanced Rasterizer platform. And that one is a highly optimized, and it uses vector instruction, it uses parallel code. It's an emulator for DirectX 11 GPU. And as you saw in the demonstration, it's depending on your problem. It might be better to just write C++ AMP code and let C++ AMP fall back automatically to warp. That might be more performant than writing your own software implementation of your algorithm. And yeah, in the future, it's extensible. So in the future, who knows, maybe we can accelerate on FPGAs or yeah, maybe offsite cloud computing. Of course, then you have quite a cost of uploading it to the cloud, performing the calculation and downloading it again. But all these things could be possible in theory. And they support something called a heterogeneous mix of accelerators. So if you have a machine with an AMD GPU in it and an NVIDIA GPU, then C++ AMP can use them at the same time and distribute the load over both of these accelerators. So what is faster? If we are talking about a 2 or a 3x performance increase, that's just a little bit faster. You can either you do a little bit less work, you do a little bit more work, or you wait a little bit less for the same amount of work. but you're not going to rewrite your application or change your architecture or anything. If you're speaking about 5 or a 10x performance increase, that's already starting to become significant. So you might start considering rewriting parts of your algorithms or parts of your applications. But yeah, that's pretty much it. But if you're talking about a 100x performance increase, and that's something that you can reach with using C++AMP, then that's actually a game changer. Then you might consider changing your complete platform or re-architecture your complete application. And here are a couple of problem domains that's coming from NVIDIA. It gives some idea about the possible performance increases that you can get. So if you're doing a lot of financial simulation, my pointer is not really working, then you get an almost 150x performance increase. And even things like the string matching in the lower right corner, you can get a 30x performance increase by running it on GPUs. So it doesn't have to be always graphics related. It can be completely different. Just a little bit about the difference between a CPU and a GPU. So a CPU has, compared to a GPU, a much lower bandwidth. The GPU really has extremely high bandwidths. The CPU, you have these 4 cores, 8 cores machine. If you go to a Xeon, it has, I think, 16 cores, but that's pretty much it. A GPU, you're talking about like 1,000 or 2,000 computing units. So that's highly parallel. The CPU, of course, supports completely generic and general code because it has to run everything. It has to run your operating system, all your programs, and so on. The GPU, it really likes data parallel code. So if you have a lot of data and you have to perform something on all that data. Of course, programming for the CPU, that's mainstream for a very long time. And now with C++AMP, it's also mainstream for GPUs. It's part since Visual C++ 2012. And obviously, there is complete integration into Visual Studio. So you have all the expected debugging tools. You have IntelliSense, you have the profiler, and so on. And the Microsoft implementation is built on top of Direct3D, but this is not in the standard. This is not a requirement. So the AMD implementation, for example, targets OpenCL. It translates C++ AMP code into OpenCL. So that's for the introduction. Let's go now a little bit more technical, a bit more interesting, I assume. It's the first thing you have to do. Everything is in one header file. You just have to include the amp.h header file, and it's in the concurrency namespace. There are a couple of new classes, 6 actually. You have an array view. That's for representing your data. You have an extend to represent the size of your problem domain. You have an index, which is a point inside your space that you're working on, and then you have an accelerator view, which allow you to query information about your accelerators. There is only one function, parallel for each. There are, as I said, 2 new keywords, the restrict and the tile static. I'll come back to all of these on next slides. The first one is the concurrency array. It's a template. It has 2 template type parameters. It's the type and the dimensionality. So the type is the type of the data that you want to store in your array. And the dimensionality is it a 1-dimensional array, 2-dimensional, 3-dimensional, and so on. It can go up all the way to 128. That's pretty hard to visualize, but it is possible. And if you construct an array, you have to explicitly call the copy method to copy the data to the accelerator and to copy it back to the CPU. Here is an example of a 1-dimensional array of 10 floats. So you specify the type here. You say that it's a 1 dimension, and in the constructor argument, you specify how many elements you want in that 1-dimensional array. Here is one of a three-dimensional array, so you of doubles, you specify double, it's 3-dimension, and then you specify the size of each dimension. The next one is an array view. Array view. It has the same template type parameters, so type and dimensionality. What this one does, it's not allocating any memory for you. It's actually wrapping your memory so that CppAmp can use it. And the nice thing about this is that it will automatically transfer the data from your user allocated memory to the accelerator in the beginning of the calculation, and at the end it will automatically copy it back to the CPU. It's something else, it's the array view is, and the array also is dense in the least significant dimension, and that will become clear on one of the next slides. An array view, it wraps a user allocated array. So you can make a read-write array view. That's just like on the previous slide. But you can also make a read-only buffer. And that's simply by specifying const here. And by doing that, you're actually optimizing the code because it's a read-only array, so you will not change anything in it. That means that CppAmp only has to copy it in the beginning to the GPU or to the accelerator, but there is no point in copying it back to the CPU at the end because it's read-only, so it cannot change. And the opposite is also possible. You can have a write-only buffer. This one you have to define just as you would define a normal array view, but then you immediately call the discard data method. And again, CppAmp can optimize this. Oops. So since it's write-only, there is no point in copying some data that will be written over anyway from the CPU to the accelerator. So this one will only copy the data at the end of your calculation from the accelerator back to the CPU. Here is a graphical representation of the extent class. So extent is, it represents the size of your space. It's an n-dimensional space. So give 3 examples. So this one is a 1-dimensional extent of size 5. You have a 2-dimensional one there and a 3-dimensional one on the right. And you see they are dense in the least significant dimension. So the least significant dimension is a 4 here. So you see the 4, they are next to each other, so it's dense in that dimension. Then we have that index class, which the extent and the index, they belong together. They work together. And the index allows you to define an n-dimensional point inside your n-dimensional space. So in this case, you're just defining this red square, and here also. So again, this is also, first you have to specify this dimension, and second, the horizontal dimension. So the least significant one is the dense one. Then I said there was only one function that you can call for CppAmp, and that's this parallel for each. That's your entry point into CppAmp. It requires 2 parameters, just the extent, or your space in which you're working, and a lambda function. And the extent that you specify here, that's also used to decide how many threads CppAmp will launch on your accelerator. The lambda, this one has to be marked as being restrict amp as such. And that means that the compiler will verify that you're not doing anything inside your lambda that will not work on a GPU. When this line executes, it will send the work to the accelerator. It will immediately return, so it's not blocking. And so the rest of your code following your parallel for each will run in parallel while your GPU or all your accelerators are doing the work. Because it's non-blocking, you have to remember that your lambda that you pass in, you have to capture everything by value. or except for concurrency array object, they have to be captured by reference. Here is a very simple example. It adds two arrays together. You have an array A and B with a certain number of elements in it, and we want to calculate the sum of it. So that's pretty straightforward, just a simple loop. If we want to convert this to AMP, first thing you have to do is include the header file. Let's just add a using namespace here. Then we convert our input arrays into array views so that C++ AMP can make use of them. Since this will calculate A plus B equals sum, so A and B are read-only arrays, so we define these as array view of const ints of one with dimensionality of 1. The sum, on the other hand, is write-only, so we immediately call discard data. Then we call our parallel for each, and we specify the size of our space that we are working on, which is simply the extent of our sum in this case. Okay, that's the restrict amp keyword that I was talking about, and on one of the next slides I will explain what kind of restrictions there are. There are actually quite a lot. Inside your lambda, you have a parameter, an index into your space, and this one you can use here to perform the calculations. And as said, the array view will automatically copy the data from the CPU to the GPU and the other way around when the calculations are finished. So what about these restrictions? If you mark a function or a lambda as restrict amp, then it can only call other restrict amp functions. It has to be inlineable, and you can only use a few data types: int, unsigned int, float, double, and bool, and structures and arrays of these. So that's already quite a lot of restrictions, but that's not all. Actually, this is the whole list of restrictions, so things like recursion, virtual functions, pointer to functions, all that stuff is not allowed. Go-to label statements are not allowed, but they are actually also not allowed on the CPU. Yeah, exceptions don't work. Obviously, assembler you cannot use, and there are lots of restrictions here. And this keyword, the restrict amp, is actually part of the signature of your function, so that means that you can overload on it. Here we have a function foo that is restrict for the CPU and AMP at the same time. So that means that this function can be executed on the CPU or on C++ AMP. But you can make a distinction. So we have a function bar that is overloaded only on the restrict keyword. The first one will be used when you run it on the CPU. The second one will be used if C++ AMP is using the function. Now, I didn't say anything about error handling yet, so let's fix that. So when the parallel for each code is called, then it will immediately return and it will send over the work to the GPU. So at one point, the CPU will block to get the data from the GPU, and that's called a synchronization point. And there are actually 3 ways to have a synchronization point. You can either do it manually by calling the array view synchronize, and that's the recommended way. So because at that point you can perform your error handling. I will show that in an example code later. There is also an automatic synchronization point. So whenever CPU code is observing your array view that you gave, then it will block until your accelerators are finished with calculating it. But if there is no try-catch block at that moment, then you will lose all exceptions that might be thrown by C++ AMP. And the third one, and that's the worst case, there is a synchronization point when your array view goes out of scope. And that means that the destructor of your array view will actually block until the GPU is finished or until the accelerator is finished. But a destructor is not allowed to throw any exceptions, so they will be completely silently ignored, and this is the worst case. So best case is to manually synchronize and have a try-catch block around it. We have these two helper classes, the accelerator and accelerator view. These allow you to query all the accelerators that are installed on your machine and to ask if they support single-threaded, single performance, single precision floating point operations or double precision floating point operations and so on. And this is a very simple example. It just gets all the accelerators in your system and just loops over them and writes the description to standard out. There is this thing called tiling. This is a pretty advanced feature of C++ AMP, so I'm not going deeper in on this. Basically, you will split your work in smaller batches, then so that they fit in a faster cache on your GPU. Then you can get much greater performance increase. But yeah, there can be some race conditions, and it's much more complicated. So that's for another presentation. Let's see how we can write a C++ AMP version of a Mandelbrot renderer. So this is straightforward single-threaded implementation. It just loops over all the rows in my image, and for each row it loops over all the pixels in it, and then here it calculates a Mandelbrot value for each of these pixels. If you want to convert this to a CPU parallel version using Microsoft PPL, it's actually very simple. I'm not sure if you saw what changed, but it's basically just this. Instead of having a normal for loop, you just write parallel for. You say that it has to loop from minus half height to half height with a step size of 1. And then the body of the original for loop, you convert to a lambda. And that's basically it. And at the end, you have to close your parallel for function call. I just noticed that I'm capturing everything here by reference. It's actually not recommended to capture everything automatically by reference or by value. It's better to explicitly state what you want to capture so that you don't have some strange problems with that. Now we have the PPL version. Now we can convert this one to C++ AMP. First thing is we convert our array, our buffer to an array view, so C++ AMP can use it. This one is just calculating a Mandelbrot image, so it's write only. So we immediately call the discard data in our array view. Instead of parallel for, like for the PPL version, we call parallel for each. We specify the size of our two-dimensional image, and then we convert, and then we have our lambda expression. This one is a two-dimensional image, so we have a two-dimensional index here. So the first thing we do is we convert our two-dimensional index to an x and a y, so that I can use it in the rest of my calculations. Then you cannot use the normal mathematical functions like logarithmic and square root. You have to use the C++ AMP version, so there are two of them. Here I'm using the fastlog and fastsqrt. Those are single precision versions of those functions. If you want double precision, then you have to use the ones from the precise math library. But not all GPUs support double precision, so you will have to check using the accelerator and accelerator view classes. You have to check if your accelerator is supporting double precision or not, and provide for a fallback if you want. So then we calculate our value for a certain pixel, and we store it in our array view. And the last one, like I said, the recommended way is to manually synchronize. And that is a place where we can put that's for our error handling. So we have our synchronize here, and we just put a try catch around it. Here we can react to exceptions thrown by C++amp. So if you don't do the a.synchronize there, then you will lose these detailed exceptions. So let's see how it looks like. Oops. So now it's the S button. Yeah, this is programmer art, so it's not really beautiful. This is the S button for single-threaded rendering. At the top here, you should see. I cannot see it. But yeah, so it takes 500 milliseconds. It's a very low resolution, this projector, so it's not that slow. But yeah, it's not really interactive, as you can see. If I switch to PPL, that's already much more interactive, and I'm getting like 78 milliseconds for each frame. Probably not going to get too much performance. Yeah, still half. But that's because the resolution of the projector is pretty low. If you render it on a much higher resolution, then the difference between the single-threaded, the PPL version, and the C++amp version is much more pronounced. But yeah, now it's perfectly interactive. Thing is, this is the single-threaded version, so if I zoom in long enough, so that's the single precision version, so you start seeing artifacts. If you don't want this, you need to implement the double precision version if your GPU supports it. So a couple of words on Visual Studio integration. Of course, it's completely integrated in Visual Studio since 2012. You have all the things that you want. You have CPU, GPU, breakpoints, even simultaneously, but there are a couple of restrictions there, again. You can inspect all the GPU threads that are running. You have the parallel stacks window, the parallel watch window, and the concurrency visualizer. So GPU breakpoints are supported, but if you're running Windows 8 or Windows 7, you have to make a choice. You can either put a breakpoint on CPU code, or you can either put a breakpoint on GPU code. And you have to tell the debugger what you want. So here you specify if you want native only or GPU only. You cannot have both. But both are possible with restrictions. So it requires Windows 8.1. Windows 8 will not work. It requires 8.1. It requires at least Visual C++ 2013. And you have to use the warp driver, so the software emulator. And that's in your project properties, you have to specify explicitly that you want to use the warp software accelerator. When doing that, then you can have multiple breakpoints in CPU code and in GPU code. So here in this example, the first breakpoint is obviously in CPU code. It's on a try line. The second breakpoint is inside my parallel for each, so that's inside GPU code. When you break at that point, you can inspect all your GPU threads. At the bottom here, you see in this particular case, there are 256 threads active. And for each of these threads, you can inspect the local variables that's in this window. So you can see what each thread is computing. There are lots of threads, of course, going on. Here there are only 256. 4 of them are blocks for some reason. But on different hardware, you can have like 1,000 threads or 2,000 threads. So it's possible to flag them, filter them, group them, or to freeze certain groups of threads and unfreeze them, and so on. I mentioned the concurrency visualizer. It used to be included with Visual C++ 2012, but it's not anymore in 2013. But you can just download it from the Visual Studio Gallery and install it. And I recommend to give it a try. It shows you the activity not only of the GPU, but also of all your CPU cores. You can use it to look at performance bottlenecks. You can use it to investigate how much time you're wasting copying your data from the CPU to the GPU, and the other way around. Yeah, you can see if threads are blocking each other and so on. It's a very interesting tool if you're doing parallel code. Here is a simple screenshot of the Mandelbrot program that was running. So first, it is rendering single-threaded, so you see there is only one core that is doing any work, and the GPU is completely silent. It's not doing anything. Then I switched to GPU rendering and moved around a little bit, interactive, and here it's just rendering one frame, so you barely see it. Here it's rendering while moving. Then you see the CPU is not doing anything in that case. So C++AMP, it allows you to make use of heterogeneous accelerators like NVIDIA, AMD, Intel, and so on. And well, you saw the examples there. It's not that hard. Of course, it depends on your problem domain, like the Mandelbrot renderer, which is just calculating independently for each pixel a value. That's very easy to parallelize. Of course, if your problem that you're trying to solve is not that parallelizable, then you won't see the 100 or 150x performance increase, obviously. It's a high-level abstraction in C++, not in C. And yeah, it can use multiple vendors at the same time. And I said it's an open specification, and in fact, right after it was an open specification, Intel was working on a proof of concept called Chevelin Park. But I'm not sure what happened to that. That one was based on the Clang and OpenCL. I haven't heard anything about that afterwards. But last month, in August, AMD announced an open source implementation together with multicoreware. And that one is converting C++AMP to OpenCL, if I remember. And it works on both Windows and Linux, and maybe also macOS. So it's not just theoretically anymore. It's really an open specification. There is an open source implementation of it. So, and AMD is already proposing a couple of new features, which might get into the standard or might not. So, well, now discussion is starting about that. There are a couple of other interesting presentations about parallelism, because as said, these days all your CPUs, even your smartphone has 4 or even 8 cores these days, so you need to become parallel aware and you need to start writing parallel code. Yes, there is a question.
Yeah, sorry if you went over this in the beginning. I was in a talk that ended early. But how well does this does C++ AMP interact with C++ threading, like atomics, things like that?
So how well does C++ AMP interact with C++ threading library, atomics, and yeah? Well, it doesn't. So the atomics and the C++ standard threading library, that's for the CPU. It doesn't say anything about the GPU. And that kind of stuff you cannot use inside your restrict AMP code.
Do you have there's like a cost to calling some of the functions to set up the extent and things like that? Do you have a kind of a rule of thumb of like the number of elements that you might be iterating over where it would start to make sense to taking advantage of GPU? Like we say, okay, well, if I've got like 100 ints, then yeah, I should start considering putting this over to C++ AMP, or if we're talking 1,000 or 5,000. So do you have any rules like that you would recommend?
So no, there are no rules like that, because it's less important how big your extent is, or well your array is, but it's more important the calculations that you're doing on it. of course, if the best way is to profile it and to use the concurrency visualizer. There is not really a rule of thumb for that, no. So you can use a concurrency visualizer to see how much time you're wasting copying the data to your accelerator and the other way around. But there is nothing like, yeah, for 100 elements you can do it. Less than 100 you don't do it. No, unfortunately not. No.
So you mentioned the Intel working with OpenMP. So can you go into any details about the implementation of this?
The Intel version?
You mentioned Intel, was it?
Yes.
The transfer to OpenMP to
No.
not OpenCL.
OpenCL, yeah.
So what are you transferring to?
Well, I don't have much details about it. I just read somewhere that Intel was working on a proof of concept. I'm not even sure if it's public. They were just trying to do it. What they do is convert C++ AMP to OpenCL code, and then that one is running on the GPU.
Yeah, but what are you doing? What is Microsoft doing? How does that work?
Microsoft is converting it to direct compute, so it converts it to, I think, HLSL, high-level shader language kernels. Yeah, so the Microsoft implementation requires DirectX11 GPU, but the Intel implementation or the AMD open source implementation, they don't necessarily require a DirectX11 GPU.
So my question is related to that. So the code that's generated by the compiler is embedded in the compiled image. This non-CPU code is embedded in the compiled image. Is that right?
Yes. So the CPU AMP code is, for Microsoft, I think, converted to HLSL, and that's embedded inside your executable. Yeah.
All right, I got a couple of follow-up. Does this work with just 32-bit code, or does this work with 64-bit binaries too?
It works with both of them. Yeah.
With both of them.
Yep.
And then if you let's say you're building this on with 64-bit binary, and you've allocated a huge chunk of memory that's maybe more memory than can fit in the GPU. I don't know much about GPUs, but let's say it's just more than you've got available on your GPU.
Mm-hmm.
Is that going to just take parts of the job and do parts of the job, or is that just going to fail?
That's a good question. So what happens when you allocate a buffer that's too big to fit on the GPU? Not sure. I would expect it to throw an exception.
Okay, so it's not like it would just say, all right, I don't have n bytes, but I have half that on the GPU, so I'll just take half the job and start doing
No, it will not do that automatically, but that's what you can use a tiling mechanism for. So you can break up your problem into smaller tiles.
Okay, so that's a tiling job.
Yeah.
Okay, thanks.
And these days, some GPU cards have already upwards of 8 gigabytes of memory. So you really need to allocate a very big buffer to hit that limit. But yeah, of course. Yeah, it's possible. Yeah.
Is there any special treatment for sparse matrices to avoid copying all the data across to the GPU and back?
Is there any special treatment for sparse data? No. So it's just copied. Everything is copied.
Copies everything.
Yeah. So on Tuesday, it's an interesting day for if you're interested in parallel talks. We have writing data parallel algorithms on the GPU by 8 Miller. We have a talk about OpenMP for GPU accelerators and other things by Michael Wong. And we have decomposing a problem for parallel execution by Pablo Halpern. So that's what I was mentioning. C++ AMP is easy to use, or PPL, Microsoft PPL or Intel TBB are easy to use if your problem is easily split into parallel workloads. If that's not the case, then you have to redesign your problem and try to make it parallelizable. I also want to mention this book. There is a great book written by Kate Gregory and 8 Miller. It covers everything of C++ AMP, including the advanced tiling stuff. So if you're interested in that, you should get a copy of this one. I think it's available in the bookstore. It is? Yeah, okay. And if you're interested in learning more, there are lots of resources, and there are on this website. You don't have to write this down. I think the slides will be shared afterwards. There are like 36 samples that you can use of all kinds of things, like visualization problems or even non-visualization problems. So, and if you have any problems or suggestions or comments or whatever, you're always free to contact Sharma Raman, which is the program manager of C++ AMP. So that's what I had. If there are any more questions.
Do you have any plans, or you know if there are any plans to incorporate something like C++ AMP, or C++ AMP itself, or something like it into C++ the language? Is that in the cards or not?
So the question is if there is any work on implementing something like C++ AMP in the standard. They are working on adding parallel stuff to the standard. There is something they are thinking about, something with policies. So, for example, if you have the STL algorithms like std sort, you can give it a policy and tell it run this sequentially, single-threaded, or run this multi-threaded. And this policy is also vendor. The vendor can change these policies. So, for example, a Microsoft compiler can add a policy to run it on C++ AMP and things like that. So, yeah. Yep.
Hi, I'm Michael Wong. I might be able to answer that question. The standard is adding parallelism in the library purely using by creating parallel algorithms for standard template libraries that can have different policies attached to them. As you said, they're either vectorized or vectorized and parallelized, or what's called vecpar, or sequential. And theoretically, it is possible to add something that says GPU acceleration, depending on what the library depending on the library. If we're talking about language itself, now much of this obviously is library-based. If we're talking about adding capabilities to the language itself, a la like C++ AMP, Herb's comment was that it's still too new yet at this point for him to try to put it into the standard, which is pretty consistent with what I think it is. I think there's a lot of different options there. You talked about some of them. I'm going to talk about how OpenMP does it. They all bring in different perspectives. So it's important for us to gather a lot of the data in order before we try to solidify it into the standard. So sorry for interrupting. I just thought that might help the discussion.
Interesting, yeah. Thanks. So, okay, if there are no more questions, then thank you for coming here.